right, we've only got 2 cells left in our table to fill out. Our last 2 pieces of information that we're interested in identifying are, how do we find the roots and the vertex if we are in standard form? These ones are going to take more work than the rest, but the good news is that the work that we're going to do, we are only going to do once, and we're going to allow that work to represent a shortcut for us, so that these don't actually take work in the future, but it is going to take a little bit of effort on my part to help set these guys up here. So let's motivate this by looking at an example. The first example I'd like to look at is this quadratic in standard form. Y equals x squared plus 6x plus 8. Our goal in this case is, let's go ahead and try and identify the roots here. What we're going to end up finding, by the way, is that identifying our vertex information from standard form, we're going to get this piece of information along the way when we compute our roots. So we're just going to focus on finding the roots for now, and we'll see that we can also extract our vertex information from that. So my question to you is, could you find the roots of this quadratic here? And here's what I know. I can't just look at this and identify the roots. I can't just set y equal to 0 and begin solving, because I have 2 different instances of x that I can't get together. Typically what I like to think to myself is, since I have 3 formats of quadratic equation, the question I want to know is, which of these is going to be the most helpful to me? I know that if I'm looking for roots, I'm always hopeful that I could be in factored form. Factored form is built just to talk about roots. So my question is, can we factor this quadratic? If we're going to be able to factor this quadratic, then I need to be able to break down 8. I'm going to come up with my product pair list for 8. 1 and 8, 2 and 4. It seems to be all the choices that we have. We'd like to choose the pair that has a sum or difference of 6. And by the way, I'm noticing that since all terms are positive in my quadratic here, it better be that we're using only positive numbers in our breakdown. I see that using a positive 2 and a positive 4 is going to be an appropriate breakdown for 6. And that's going to allow me to immediately factor this into x plus 2 times x plus 4. This makes it really easy for me to identify the roots. I know that x-intercepts occur when y is 0. And now we have the 0 product property. 2 terms together are multiplied to give 0. Therefore, either the first term is 0 or the second is 0. So it looks like one of our strategies associated with finding the roots of a quadratic in standard form is to say factored form is the format that we actually like. So even though we're in standard form, our move is going to be to say get into factored form. From factored form, identify your 2 roots. But we're going to see that we're going to end up with a little bit of a problem with this. Hopefully what you've identified by now is that a lot of the quadratics that I set up for us to factor are set up very nicely to be able to be factored. So let's go ahead and take a look at some other possible scenarios here. So we just found the roots of a standard form quadratic by factoring. Let's ask ourselves, is this the only thing that we need to be able to do? The next example I want to use to help investigate this is y equals x squared plus 6x plus 7. You should notice that this is very similar to the previous quadratic that we just looked at. I had an 8 there a second ago. It's now just a 7. So we've only changed the problem a tiny, tiny bit. Again, I'm interested in finding the roots. Again, I'm hoping that you're thinking to yourself, boy, factored form would sure be nice right now, because factored form makes finding the roots easy. And so I'm going to attempt to factor. I know that if I need to factor this guy, I'm going to make my product pair list for 7. Since 7 is a prime number, 1 and 7 is the only product pair that's possible. Again, I'm identifying that all of the terms in my standard form are positive. Therefore, it must be the case that all of the breakdown terms are also going to be positive. But what I can see here is there's no way for me to use a positive 1 and a positive 7 to make 6. It doesn't seem like there actually is a factored form for this. So we can't factor this. So what are we going to do then? We still want to be able to find the roots. I'm still reasonably convinced that this has roots. In fact, if I picture the graph of our previous quadratic, all we've done is shift this up 1 unit. It used to, down 1 unit. It used to be at a vertical shift of positive 8. Now it's only at a vertical shift of positive 7. It still opens up. I'm thinking this thing still hits the x-axis, but I just can't quite determine where from factored form. So our current situation is I can't identify the roots in standard form. I can't get into factored form to identify the roots. So our only hope left is vertex form. From our table, we've previously found that if we are in vertex form, then we just need to set y equal to 0 and solve, and we'll be able to identify our root locations. Let's go ahead and see if we can do this here. So if we recall completing the square, what we remember is that we are interested in fitting a very, very perfect format here. We're interested in fitting the format y equals x squared plus 2px plus p squared. In our case, I can see that if 6 is the same as 2p, then it must be the case that p is 3. And if p is 3, that means that the term that I actually need on the end is not 7, but instead p squared, which should be 9. This is going to inform me that the quadratic that I'd actually like to work with is y equals x squared plus 6x. I've now identified that 9 is the special term that I'd like on the end, so I'm going to bring in 9. But I can't just go add 9 willy-nilly to equations. I need to keep this fair. I can't add or subtract amounts from a side without compensating for that. So just as I have added 9, I am also going to subtract 9. And finally, I don't want to forget about our friend 7. He's just trailing along for the ride on the outside out here. The reason that I've done this move of adding and subtracting 9 is because now my first 3 terms here represent a completable square. I know that this square is going to complete as x plus 3 squared. And then these terms on the end will sort of be our garbage collection. They'll become our k term. So our first 3 terms were the completable square. The last terms on the end formed our k term of -2. Remember that our goal right now is to be able to find some roots, so let's go ahead and set y equal to 0 and solve to identify the roots here. I'm going to go ahead and move myself back up to the top. So our goal is to find the roots. We have converted into vertex form from standard form because we know that in vertex form we should be able to set y equal to 0 and solve for x. So I'll first add 2 to both sides. I'll take my square root, remembering my plus or minus, and I'll subtract 3 from both sides. And it looks like I've arrived at some roots. I'm noticing that they're not very clean roots, which is not terribly surprising to me. If I were going to get some clean roots like 4 and 6 or something like that, then I would have expected I would have been able to find factored form, which we were not. So here's the lesson that we've kind of learned from this. If you're in standard form, we'd like to be able to just factor the quadratic to get the roots, but not every quadratic is factorable. On the other hand, what takes a little bit more work is finding the roots from vertex form, but the good news is that we can always get into vertex form. We can always complete the square. It took some effort to complete the square, it took some effort to set y equal to 0 and solve, but they're both guaranteed doable processes. So on the one hand, they take a lot of work, on the other hand, it's guaranteed to be able to be done. So like I said, what we're really interested in doing here is setting up a shortcut for ourselves. What I don't want to have to do every time I'm finding the roots of a quadratic in standard form is I don't want to have to first complete the square, then set y equal to 0 and solve. It took 2 boards of work for me to do that. We're trying to avoid doing that. So what I'm going to do right now is I'm going to do the most general version of this that I can, and then we'll use our answer from this general version to use that as our shortcut in the future so that we can avoid doing this work. But again, it's very important conceptually that you understand that what we're trying to do is shortcut this process. It's a 2-step process. Step 1, complete the square. Step 2, set y equal to 0 and solve. We'd like to sort of cut out the middleman here and just arrive at our result at the end. So let's go ahead and take a look at the very general version of completing the square and setting y equal to 0 and solving a very general quadratic in standard form. So what we'd like to do is we would like to do the most general version of completing the square and setting y equal to 0 and solving as possible so that we can find the roots of any quadratic in standard form. Since this is what all quadratics in standard form look like, I'm just going to go ahead and do this procedure on ax squared plus bx plus c. The good news for you is that this is the absolute hardest that this problem could ever be made to be, and I am going to do it for you. You just get to experience the benefit of the shortcut that I'll be creating for you by go ahead and doing this process. You should still follow along here though. This is a great way to kind of confirm that you are fully competent in your ability to complete the square and set y equals 0 and solve, since again, this is the hardest that this could ever possibly be right here. And again, you won't ever have to do this. You just get to use the shortcut that is produced as a result of this process here. So my goal is to complete the square. And the first thing that's annoying me about completing the square right away is this a term that's sitting out front. So my first algebraic move is going to say, before I complete the square, let's factor out a from the relevant terms. Remember that factoring is a division process, just like distributing is a multiplication process. They're inverse processes here. When I've divided a out of ax squared, it leaves me with just x squared. When I divide a out of bx, I'm going to get a b over a x. I've divided a out of this. Importantly here, I'm also going to just ignore c. What we've kind of seen in all of our completing the square is that c ends up just sort of being part of a garbage collection on the term out there in the end. It's going to become part of our k term in vertex form. We never really have to do anything with it. It sort of just always goes along for the ride. So that's why I'm not factoring a out of my c term here. I really just don't care about c. We'll deal with it later. These are the terms that matter for completing the square. So now I'm thinking to myself, I'm trying to fit my mold for completing the square, which looks like x squared plus 2px plus p squared. What I can see in this case is that if b over a is 2p, then I can divide both of these by 2 to arrive at my value for p. So it seems like the p of interest for me here, dividing by 2, is going to give me b over 2a. And I need to know what is my p squared term so that I can add and subtract that term. So if I square p, then I should be finding that p squared is going to be b squared over 4a squared. I've squared b, I've squared 2, I've squared a to arrive at my p squared term. So let's go ahead and use this p squared term to create the third term that we want on the inside here. So I have brought in the p squared term that is needed to complete the square. This is now a completable square. It's exactly the 3 terms I want to complete the square. My issue though is I have added b squared over 4a squared to this equation. So what I now need to do is also subtract it from the same side so that I haven't added or changed the value at all. I haven't added anything, I haven't subtracted anything. There's one little tiny catch that we want to see here though. I didn't just bring in b squared over 4a squared into this equation. I brought in a copies of b squared over 4a. If you think about redistributing this a across each of the terms, we're going to get back ax squared. We're going to get back bx because a divided by a will cancel. And notice here, this is really like, if we were to multiply this a through, it's really like this term is a b squared divided by just 4a, not 4a squared. If we multiplied the a through, one of the a's on bottom would cancel. So what I need to do to remove the same term from the outside is to remove a b squared over 4a, not 4a squared. Again, this is a copies of b squared over 4a squared. If we multiply the a through, a would cancel with one a on bottom. So in reality, this term is actually a b squared over just 4a. So that's exactly what I've subtracted off on the outside to make things fair. Don't forget, c is coming along as part of the garbage collection out here on the end, so I'll go ahead and stick my plus c on at the end right there. We're essentially done. The only last step I'm going to do for completing the square, which is one of our 2 steps that we need to do, is I'm going to identify that this is now a completable square. I know that I can complete this square using our p-value of b over 2a. I'm also going to get a common denominator so I can group up these terms together on the end. All I'm going to do is recognize that c needs a denominator of 4a. So I'm going to multiply c by 4a divided by 4a. This should be leaving us with a final end term. We have negative b squared still on top. Notice here this term 4ac divided by 4a That's really just c right there. I've just got my common denominator. So the good thing that I've done now is I've worked to get myself into the format of a times x minus h squared plus k. It's certainly true that our terms are a little bit gross. That's why I'm doing this one instead of you. So notice what our big goal here is. Our mission here is to find roots, not just complete the square. So we've done step one, which is we've converted from standard form into this kind of gross looking vertex form. Now that we're in vertex form, it should be possible for us to set y equal to 0 and solve for x. It's going to be a little bit gross, but I think what you're going to see on the other end is something that you're going to recognize here. So I'm going to go ahead and move this term back up to the top, and we'll go ahead and set y equal to 0 and solve. So let's wrap up this story here. So what we started with was ax squared plus bx plus c, any standard form quadratic. We've completed the square on a standard form quadratic. To find the roots, we now want to set y equal to 0 and solve. To save a little one line of work right here, maybe I'll just go ahead and write this right now as the 0 it needs to be. What I know I'm going to start by doing is doing my appropriate addition subtraction to move this term over onto the left-hand side. I'm noticing here that currently the b squared term is negative and the 4ac term is positive, so those two should switch signs as they move across the equal sign here. So I'm going to get a b squared minus 4ac divided by 4a. That should be equal to a times x plus b over 2a squared. My next algebra move here is going to be to divide by an a on both sides. Again, I'm going to save a little bit of room right here since I got the small whiteboard. The thing I'm identifying is that on the left-hand side, this expression on top has been divided by a once. We're going to be dividing by an additional a. So as I divide both sides by a, this a is going to be canceled away by the division by a, and there's now going to be two different a's that we've divided by on the bottom. So now we have it divided by a squared. My next step that we can see is to go ahead and take a square root on both sides. Don't forget your plus or minus. And we've got a couple steps that we can do to help clean this up. Notice, first of all, that we're one step away from being done. All I have to do is subtract b over 2a to the other side, and we're done. We're just going to want to write this in a slightly cleaner way, so let's do some cleanup steps here as well. Looking over at our square root term, I really don't know what to do with this numerator. b squared minus 4ac, I don't really have a better way to write that. The one thing that I do have a better way to write is I can ask myself, do I know the square root of 4a squared? And this is good because I do know the square root of 4, it's 2. I do know the square root of a squared, it's just a. So it seems like I'm going to be able to evaluate the square root in the denominator only here, but I'm going to leave the square root up here in the numerator. Further, I'm going to go ahead and subtract my b over 2a term to the other side, and so what we should be arriving at here is x equals, I'm going to subtract the b over 2a over, so we get a negative b over 2a, plus or minus. I'm going to leave the square root parts alone on top because I don't know how to do that evaluation. And I'm going to divide by 4a squared. We've taken its square root. We should be getting 2a as our denominator. In general, this is often written as a combined statement here. You should notice the one nice favor that happened to us in this whole process is that these two kind of gross looking fractions here both already have a common denominator of 2a. So typically this is written in its most simplified form as negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. But I've actually got a good reason why I care about it, almost maybe more in this format. Before I walk away from this though, I'd at least like to say, this is generally what we refer to as the quadratic formula. And its job is to find roots in standard form. So, one, this is the shortcut that we've been working to reach here. From now on, if you're looking for roots in standard form, and if you can't factor that quadratic, then you can just identify what is your a, b, and c terms, plug them into this equation right here, do a little bit of evaluating, and you'll be able to find the x values plural because we have the plus or minus in here of your two roots. But we're not only interested in finding the roots, remember. We also came here to talk about the vertex location. So I want to talk about these two pieces here, the separated pieces. I think that this is actually a really good look at where some pieces of information actually are. So what I like to kind of think to myself here is I want to think about how does this kind of gross looking equation relate to the graphical symmetry that we know that we experience with quadratics. So here's maybe an example. Generic sample quadratic here. What it looks like this x value is telling me, this is an instruction set on how to get to the two root locations. Here's my root locations. This equation is a set of instructions as to how to get to a place. These instructions say, step 1, go to the location negative b over 2a. Step 2, in both directions, go this same amounts right here. So this is like our distance term right here. I'm going to just call this let's see here. I'm going to call this M for middle, and I'm going to call this D for distance right here, just so I don't reuse any letters that I previously used. So what this is going to say to me is go to the middle location, then go this distance both to the right and to the left, and you should land at your two roots. So I know that people are pretty typically already familiar with the quadratic formula coming into this. But what I often find is that I'll ask people, like, what does the quadratic formula even do? And people will often give me the very terrible answer of, it finds x. First of all, you should at least be able to say it finds the x-intercepts, these special x values. It's not just any old generic x, these are the roots. But the other thing that I noticed that almost all students miss about the quadratic formula is it also tells us exactly where our vertex is going to be located. Notice that negative b over 2a is exactly the x value of the vertex here. So the reason why I was more interested in finding the roots right now is because, as we've previously seen, if you know the two roots of a quadratic, then by default you must know where the vertex is. It's always going to be halfway in between. In this setting right here, we go to a location and we go equidistant in both directions to land at those two different roots. Therefore, this location must have been the center where the vertex was located. So it seems like we've identified two different things. If we want to find the roots in standard form, we can apply the quadratic formula, which is the entire thing. If we're interested just in finding the vertex location in standard form, then we can just take a look at just the first piece of the quadratic formula right here. And just that first piece, negative b over 2a, that will tell us the x value of our vertex. Finally, as we've seen in the previous examples, if we're interested in finding the y value of our vertex, we can simply take this known x value of our vertex and plug it back into our original equation and find y. So this wraps up for us now everything that we want to know about all of our quadratics. We got our last two pieces of information, roots and vertex in standard form. It took a bunch of gross work, but the good thing is that you just get to experience the result at the end, our shortcut of using the quadratic formula and of identifying that negative b over 2a, the first term in the quadratic formula, is also going to lead us to finding the x value of our vertex. So getting our last two cells on the table certainly took a little bit more work than it took for us to get the first several cells on the table, but we've now seen how we can wrap up our story here with standard form. Whenever we're looking for roots in standard form, I'm typically hopeful that I can just factor the quadratic. But what we've seen is that many quadratics that do have roots are not factorable. So this is not always going to work, but it's usually what I try first. In the event that we cannot factor the quadratic, something we can always do is complete the square to get into vertex form. Once we're in vertex form, we can always set y equal to 0 and solve for x. Fortunately, all that work has been done for us by using the quadratic formula. Remember that the quadratic formula comes from the idea of completing the square on ax squared plus bx plus c, and then setting y equal to 0 and solving for x. We just get to skip all of the meat of that content right there and skip straight ahead to using the quadratic formula here whenever we can't get a factored form for a standard form here. So I'll say use the quadratic formula. That's what should always work for us here. The other thing that we saw that's very convenient is that the quadratic formula actually holds two different pieces of information for us. Not only does it tell us specifically where the two roots are, but because of the fact that two roots always informing us where the vertex is located, since it should always be halfway in between, we can grab that first piece of information from the quadratic formula and allow that to directly lead us to the x value of the vertex if we're in standard form. So here, just like in our factored form, we can get the x value of the vertex. And in this case, we saw this came from the negative b divided by 2a term that is associated with the quadratic formula. Just by computing negative b over 2a using a and b from standard form, we can determine the x value of the vertex. And just like when we were in factored form, if we wanted to come up with the y value of the vertex, we'd simply have to take this x value that we've computed and plug it back into our original equation to get the associated y value. That wraps up for us all of the information for our table. So now it seems like no matter what format you're in, you should be able to identify all three pieces of relevant information associated with any quadratic. We'll practice a bit of this coming up. Let's take a look at a quick sample of us using the quadratic formula to help us identify the roots and the vertex of a quadratic in standard form. The quadratic that I've given here is 4x squared minus 8x plus 3. I've identified that my a, b, and c values are positive 4, negative 8, don't forget the negative, and positive 3. I would like to use the quadratic formula to identify my root locations, then we'll stop and identify what is our vertex location that's also associated with this here. So I'm just going to apply the quadratic formula using my known a, b, and c values here. So let's go ahead and do this. It looks like my first term is negative b. Since b is negative 8, the negative of b is positive 8. So I'm going to get an 8 plus or minus the square root of, on the inside of my square root, the first term is b squared. Negative 8 squared will be positive 64. You should remember that this b squared term will always, always be positive. Whenever you square a number, you get a positive number. So there should never be a negative that ends up attached to the b squared term. It will always be a positive b squared term since it's a squared term. B squared minus 4 times a, which is 4, times c, which is 3. All divided by 2 times a, which is 4. All we have to do is evaluate all of the terms that are associated with this. So let's go ahead and do that. What I'm seeing here up in the numerator, 8 plus or minus the square root of, I've got 64 minus, well, I'm thinking of this multiplication in my head, 4 times 3 is 12. 12 times 4 is 48. This is all divided by 2 times 4, which is 8. And finally, I can write this as x equals 8 plus or minus 64 minus 48 will be 16 underneath the square root, all divided by 8. And this worked out pretty nice for me here. I'm noticing that 16 is something that I do know the square root of. So I'm going to go ahead and evaluate the square root. We're going to land at x equals 8 plus or minus 4 over 8. And this is now going to allow me to take my plus route and my minus route to find each of my individual solutions here. If we use the positive sign right here, we're going to get 8 plus 4 over 8, which is going to give me 12 over 8, which is going to give me the reduced fraction here of 3 halves. Alternatively, on the other side, if we do subtraction up here, 8 minus 4 will give me 4 over 8, which we will reduce down to the fraction x equals 1/2. So it looks like I've found the two roots that are associated with this. Now, one thing I'd like to point out is that these roots here are pretty clean. There's no square root terms remaining. We perfectly evaluated the square root of 16 to be 4. Anytime that we do get any rational numbers here as our roots or even integers, this should be a good indicator to you that this is actually a factorable quadratic. What I would encourage you to take a moment to do right now, pause the video, and see if you can use the AC method to factor this quadratic. Even better, maybe without being able to factor this quadratic, could you take these two roots and determine what the factored form must be? I think these are some kind of good like backwards questions here. Can we go backwards from the roots to factored form rather than factored form to the roots? The other thing that I'd like to identify here before we wrap this up is identifying the vertex location. Since the point of this is to practice using our formulas to find this, I would like to use our formula negative b over 2a. But I'd also like us to remember that we have lots of different ways to find these pieces of information. What I know is that my vertex must be located exactly halfway between my two roots. Well, what number is halfway between 1 over 2 and 3 over 2 must be 2 over 2. 2 over 2 is just 1. So it seems like what I'm expecting to get from my answer is that the x value of the vertex should be 1, because 1 is halfway between the two roots that we've previously found. So let's go ahead and take a look at using our negative b over 2a. I almost erased, I shouldn't do that yet. Let's take a look at finding negative b over 2a here. Now notice that negative b over 2a is just the first term of our quadratic formula here. So I'm recognizing that here's negative b over 2a right here. It looks like it's just 8 over 8, which I am further recognizing as the number 1, like we had previously anticipated by looking at our two roots. But what we might still be interested in knowing is what's the y value of the vertex. So let's do that little bit of work to find the x, y location of the vertex here. So if we were going to use our formula, the x value of the vertex should be at negative b over 2a, which in our case is negative 8 over 2 times 4. The negative came built in with the formula. The negative on the inside is because b is a negative. Two negatives cancel to make a positive. 8 divided by 8 is going to give us 1. So here we can confirm that we're going to get 1 for the x value of the vertex. If we want to find the y value of the vertex, we just have to plug in x. We plug in x to find y. The x value of interest for us is 1, so let's go ahead and plug in 1 as our x value here. 4 times 1 squared minus 8 times 1 plus 3. We can evaluate as 4 minus 8 plus 3 and get our y value. 4 minus 8 is negative 4. Negative 4, positive 3 gives me negative 1. And it seems like we're going to land at a vertex of positive 1 for the x value, negative 1 for the y value here. So we can use the quadratic formula and just the first piece of the quadratic formula to help us find both roots and vertex of any quadratic that's in standard form.